Okay, thanks everybody. I'm changing gears now from the indicators. I'm now actually starting to look at diamonds these days. It's a new venture on my part, and it starts a little while back. In November 21, I gave a talk for what's called the Vancouver kimberlite cluster. John Bristow had a look at that talk. During that talk, I looked at the diamond data, in fact, the microdiamond data from a kimberlite called Tuawi, which is in northeastern Canada. And for the benefit of discussion that Andy Moore started yesterday, I've just put up the 3 bullet points here that come out of that talk, which is that small diamond xenolith nuggets are diluted in barren kimberlite in this setting over here. And it forces us to recognize that there are 2 distinct diamond populations after dilution and mixing, which requires you to use 2 grade size curves in the microdiamond population. And how that differs from current application is that current benchmarks implicitly assume homogeneous mixtures described by a single grade size curve. So the way that I'm starting to look at microdiamond populations is not really driven by geostatistical considerations, although I'm going to talk about that in this talk. It's driven by sort of petrological considerations, which is the field that I come from. So I might have a slightly different perspective on how diamonds that are contained in mantle rocks end up mixed with kimberlite, and how we then analyze those things and try to derive a geostatistical description of that process.
Herman, can I just ask a question there? Sorry to butt in, but I think it's important now.
Yeah.
When you say small diamond xenolith nuggets, so that's small xenoliths.
Yes.
Okay.
Yes.
Not necessarily small diamonds.
Yes. So it's a good question to ask at this point. So that's why I just wanted to put this up at the front end here. The Tuawi case it forces us to recognize that a small peridotite like this, which comes from Udachnaya, has an astounding number of very small diamonds, but has no macrograde attached to it. In this case, for this diamond eclogite, it's a very small xenolith. You can see there's 1 centimeter over there. That's 5 millimeters up there. This particular fragment of the mantle is an eclogite. It has 30 diamonds in it in a completely different size range, 0.8 to 3.4 millimeters. Those are slightly commercial diamonds, and the macrograde of this thing is enormous. If you take these 2 fragments of the mantle, which both contain diamonds, and you start mixing them, and in fact, you dilute them in kimberlite, in barren kimberlite, then you can end up explaining the type of microdiamond distributions that you see at Tuawi. And so from a statistical point of view, these diamond-bearing pieces of rock are nuggets, and from a petrological point of view, they are small diamond xenoliths. I hope that clarifies just these 4 words that are over there. So let's start the talk by just pointing out that I have previously spoken fairly recently about this topic, in particular March 2019, when COVID came around to Canada at PDAC. I gave this talk, and so it's pretty much forgotten in the fog of the past 2 years. And we spoke about macrodiamond benchmarks, precisions and errors, and examples, several of which are repeated in the current talk today. But I wanted to put up this graph that came from that talk. And it's an important graph to bear in mind when you start talking about microdiamonds. in 2001, National Instrument 43101 in Canada, version 1 of that instrument, came into effect as a result of the Briax gold scam, which was perpetrated by way of the Vancouver Stock Exchange at that point in time. And what NI 43101 caused is a set of disclosure related in particular to the junior mining industry, but it has now crept up in brackets to sort of mid-tier producers as well. Fairly soon after that, the Canadian Institute of Mining and Metallurgy instituted this thing called Route 2 sieve reporting for microdiamond results, and standardized the way junior diamond explorers were to report their microdiamond results, because microdiamond results are considered material information. And so as a result of these two events, the amount of microdiamond data that was being disclosed in the public domain in a standardized format, Route 2 sieve format, it just skyrocketed. It took a dive after the financial crisis. So in the post-GFC period, it became much lower, but since then it's picked up again. In addition, as you can see in the brown bar graphs here, the public bulk sampling results, which were reported in DTC sieves and by ton, has become disclosed as a result of NI 43101. And you'll see the shape of this curve is roughly the same as the shape of this curve, but it's displaced 2 or 3 years later. And that's the exploration cycle. You first get your microdiamond results, and then you follow up the ones that are of interest. And these two data sets combined, microdiamonds and the bulk sampling result that goes with a set of 3-year earlier microdiamond results, it becomes a data set that you can recompile and then make these macrodiamond benchmarks out of them, which is something that I then went into and started looking at precision and errors that's related to combining these two data sets and making benchmarks out of them. The other talk, as I just alluded to, was 2nd of November 2021. It has a lot more to do with what we see in terms of microdiamond distributions at low counts, because at low counts you start seeing nuggets much easier, and as a result you're being forced to consider the contribution of geostatistical nuggets to the total microdiamond content from particular kimberlites and into Huawei. That takes on a whole new meaning. That talk is actually recorded. It's on YouTube, so I'm not going to spend any time on that. The focus for today's talks, just this one single talk, is just these 4 topics over here. I'll put on some context which comes from a Journal of South African Institute of Mining and Metallurgy publication, 1973, Herbert Sichel. I'll rapidly move on to Debbie Bowen's disclosure around Letseng Terai in Lithos, and then we'll look at the stuff that was discussed at PDAC in 2019. There is bonus for those people whose brains aren't fried by the end of this, and we'll do a straw poll at the end of this talk to see whether we want to cover that. So let's get going. This looks like a lot to consume in the first slide, but it's the only slide I'll show about that paper. This is a very important paper to go and look at if you're interested in microdiamond or, in fact, diamond size distributions. It's publicly available. It was written by Herbert Sichel, who was a geostatistician at Wits University, and it was written on commission of Anglo American, and the acknowledgement is in this paper. I just didn't copy it out. Herbert Sichel was a colleague of a guy called Dani Krige, and Dani Krige is the godfather of a technique called kriging. The two of them together were a powerful force in geostatistics at WITS in the early 70s. So good pedigree, South African, and it's useful to start reading just this paragraph on the left. How do you eat an elephant? Is one bite at a time. So let's go through this slide one bite at a time with the aid of a laser pointer. Let's look at this first paragraph over here. The cumulative percentage frequency distribution of stone sizes as given in table 3 for block X, that's the D beach. We're talking about alluvial diamond size frequency distributions here, is plotted on a logarithmic probability paper in a paper written by a guy called Tinus Westerveld, 1972. So this is the context for the current paper. The almost perfect straight line plot corroborates the remarks made previously that diamond sizes in marine deposits of Namibia are well represented by a 2-parameter log normal distribution, provided the stones originate from a small compact mining block on one and the same beach horizon. These are very important words. The 2-parameter log normal distribution that we often use in diamond size distributions has a rider on it. And the rider is that you're dealing with one population. And in this case, we're talking about alluvial diamond size distributions. And we are currently applying those to kimberlites, but that's another story. So as this paper then goes further, they say they bank this observation that was made earlier by Tinus Westerveld. And they go on to their current data set that's discussed in this paper. A further interesting example is shown as curve A in figure 1 and in table 4. So there's table 4 and there's figure 1. They say the 204 sizes listed are all of stones originating from a single 5 square meter trench section. So this data is from one locality and one very specific locality. The plot A is linear on log probability paper, and the chi-square test in table 4 is satisfactory. There's the chi-square test over there, indicating that the 2-parameter log normal distribution holds right down to a small and very exceptional diamond concentration. There's the data, 204 stones. This is how it plots on this diagram over here. It's one population. Because it's alluvial, it's size sorted. It represents a log linear plot, that's this linear line, and represents a log normal distribution that can be described by 2 parameters. These are the 2 parameters over here. This is the standard that we use even to this day for many of the diamond size distributions that people are working on are log linear plots, a 2-parameter log normal distribution. Not that complicated. It's a straight line fit on a log-log graph or a log cumulative graph. But now things take a turn. In the next paragraph, Herbert Sichel says this: in contradistinction, graph B in figure 1 represents the cumulative frequency distribution of 1,022 stone sizes given in table 5. Here they are over here. Here's 1,022 data points. The graph in figure 1 is convex and curves strongly towards larger stone sizes, indicating a compound log normal distribution. That's this graph over here. In consequence thereof, equation 28 was fitted to the data, which is a compound log normal distribution. That's the equation that we fitted to the data. And the parameter estimates are given at the bottom of table 5. There they are over there. The chi-square test indicates a very good agreement between observations and theory. This is a 4-parameter compound log normal distribution. Very few people that are currently working with diamond data sets are actually fitting their data with compound log normal distributions. You need compound log normal distributions if you have more than one population. You can end up with more than one population if you're sampling in 2 different areas, or if there are more than one populations in your underlying data set. Often it's sufficient to describe a curve like this with a single linear plot on log cumulative frequency space, and with 2 parameters, as is the case over here. But right in the early part of the development of this technology, Herbert Sichel had already seen sufficient evidence from marine diamond deposits where they're mixing differently sorted diamond populations to introduce the compound log normal distribution. A lot of us have forgotten about the fact that this exists, and that we have the capacity to describe multi-population diamond data sets. And it's right there in a paper in 1973 that was commissioned by Anglo American. So, as a result of reading this paper and paying a little bit of attention to what is being said here, we can now go and look at one of the best size distribution graphs that's been published of late. It's the one that comes out of the paper by Debbie Bowen and other authors, including John Ward. It was published in 2009. There is no other size frequency distribution published in the public domain like it. It is unique in the sense that, let's read the caption over here. Figure 3. Diamond size frequency distribution for the main and satellite tapes and Letseng total production, 200,000 carats on one graph over a period of 4 and a bit years of production. This is a very true representation of the diamond distribution in these exceptional kimbolites in Letseng. In addition, there's a very important bit of information here. The recovered Letseng diamonds average about 1 carat per stone, and the important information is what the bottom cutoff is. At a 2 millimeter bottom cutoff, and 2 millimeter square mesh is 0.14 carats. That's my number. If you look at this graph, it starts at 0.14 carats. There's a 2 millimeter square mesh sieve right there. This is the starting point for this diamond size distribution that you see over here. So you have to ask yourself this question. If you had to fit this diamond size distribution, which by the way is the only one that's published that goes into the 100 carat size range and approaches the diamond size distribution for 500 carat stones. There is no other diamond size distribution published like this. Then you have to ask yourself this question. Do you want to fit it with a curve that looks like that? Or do you want to fit it with a curve that looks like that? These two graphs are essentially the same graphs. There's carats per stone. On the x-axis, this one's just given in cumulative frequency. This one is a different version of cumulative frequency, percent carats larger than Z. If I judged by eye, I would much rather fit this curve with a compound log normal curve than I would with a straight line curve. However, we can break it down into straight line segments. That's what that looks like. There's 1, 2, 3, 4. Very simply put, from this perspective, there are 4 diamond populations represented in this size frequency distribution curve from Letseng. you can break up this curve into four 2-parameter log normal distributions. 1, 2, 3, 4. Or you can try and fit all this data with a complicated fit sequence. The choice is yours. I think it's undeniable that you cannot use a single 2-parameter log normal distribution to describe this data set, no matter what you do. That's fairly obvious. The next thing to point out on this diagram is that microdiamonds in general are less than 2 millimeters in size. In other words, your microdiamond data set is going to be sitting down here in this part of the diagram. And I want to use this diagram just to explain the benchmark concept. So if you happen to have a microdiamond size frequency distribution that is a straight line at less than 2 millimeter sizes, you'll be able to use those microdiamonds to predict this part of the curve up to about, I don't know, up to what's that? That's about a carat in size. And from there onwards, your prediction would be wrong, because you're using a 2-parameter log normal distribution. In order to have a reasonable representation of what might be going on the coarser stone sizes, you actually have to have some data. And those data come from macro size frequency distributions that we get out of bulk sampling programs or mini bulk sampling programs. And they often go up to about 6 carats, and occasionally you might get up into the specials class. So 10.8 carats is over there. There's the 11 carat mark. And in this case, if you had to do that for a thing, you'd end up with a bulk sampling results that will fall somewhere along here. And if you then integrate your microdiamonds from, let's say, with your macrodiamonds in your bulk sampling program, you will get a curve that has a step function in it over there, and it starts bending towards a coarser stone size distribution over there. And if you use that as a benchmark and do a propagation of it, then you might have a chance of predicting a part of this curve over here, but you will definitely not predict in a true fashion what's going on in this part of the curve, which is these special type 2 diamonds that come out of, let's say, because they are a completely different population of diamonds. They are not represented in this part of the curve. So anybody who is going out there and saying, oh, we can use microdiamonds to try and constrain this part of the data set, I think they're speculating. They're not following the published data that we know that is representative of the Letseng system and the different types of diamonds that are present in that system. But we've now developed this benchmark concept, which is you take a microdiamond data set, you correlate it with the macrodiamond data set that is spatially coincident and part of the public domain data set. You might get up to about 10.8 carats in that process. And the predictive power may be a little bit beyond that, but it certainly wouldn't go into the 100 carat mark. I never intend that it would be used in that way. So I'm going to just leave that there and go look at which macro diamond benchmarks do we now have currently available to us as a result of the public data set that I've compiled. And there they are. I can't remember, we have about 30 benchmarks right now, covering the range 3 carats per 100 tons to 680 carats per 100 tons. So 3 carats per 100 tons would be down here. 680 would be up here. That's Argyle, by the way. This is some other low-grade stuff. And we can make some observations on this grade size on this graph over here. It's a grade size plot. It's not a size frequency distribution plot. So grade is diamonds per ton. That's the grade portion. Size is mean diamond size. That's on the x-axis. The y-axis is assay counts per ton, diamonds per ton. There is no unit interval normalization. This is very important. A lot of people use something called Spitui plots, stones per ton per unit interval. I've removed the unit interval, and I'm able to do so because all these data have been converted to root 2 sieve classes. The advantage of doing that is that the distance between 2 points on this graph is constant. If you have root 2 sieve size data, then your data points are equally spaced on a log scale. That's very important in terms of fitting curves and being able to predict them reliably to coarser stone sizes. The x-axis covers the range from micro to macro diamond weights. So microdiamonds are down here, up to about sort of 2 millimeters, something like that. The macrodiamond weight range goes through sort of the 1 carat class. And you'll notice I stop all my curves at 10.8. I never put them any further because the data simply doesn't support it. Some of these curves stop at less than 2.8, at 10.8. That's around the 5 carat mark. And some of these curves actually stop at about 2 carats, because I simply don't have data to extrapolate beyond that. Any extrapolation beyond that is, in fact, an extrapolation. It's not a fit to the data. So a grade benchmark then is a congruent micro and macro diamond data at a known recovered grade. It's an empirical fit, which is treated as one homogeneous mixture of diamonds. It is not a model. This is a fit to the data. We have 30 benchmarks, public domain data collated to end 2018. And just a remark that was first made by a guy called Ed Hotan in Anglo-American Research Labs. He said, you cannot recover a fraction of a diamond. There is a count rate threshold that occurs at 1 stone per sieve. Those thresholds, I'll show them to you in a moment. In fact, that's what's happening next. There's 1 stone per sieve in 8 kilograms. There's 1 stone per sieve in 200 kilograms. There's 1 stone per sieve in a ton of rock. That makes a whole lot of sense. This data point over here relates to the fact that you're going from 1 to 10 carats on a log scale. If you want visibility of this part of the data set in your sampling program, then you have to have samples that are about 1,000 kilograms for microdiamonds. If you want to constrain curves in this part of the spectrum, your sample sizes have to go above 200 kilos. Typically, in the current environment, we use 200 kilogram sample sizes. I had a lot to do with that in terms of BHP, and I'll acknowledge that a bit later, which gives us visibility up to this part of the curve, and you can start projecting from that beyond. If you take small samples, your visibility or your reliable data set will be restricted, and you will only be seeing things that are in the higher grade spectrum of the microdiamond data set, definitely not the lower grade spectrum. Okay, so let's look at some real data. This came out of the Snap Lake system, quite an interesting one, 96 to 99. And it has to do with the amounts of diamonds you recover as a function of sample weight. Early on in their exploration history, they took surface samples, they took small samples, mostly less than 100 kilos, that's in blue. And by January 99, they did a mini box sampling program and with correlated microdiamonds. And some of those samples were up in the higher weight category, microdiamond samples. And then in August 99, they launched what they called the value recognition program, which entailed 3 or 4 core drills running night and day to recover microdiamond data, recover core from depth in this sheet-like system. And they had very small intersections in the Snap Lake sheet, which provided small sample sizes, but the Snap Lake sheet varies in thickness, and they had other microdiamonds that came from thicker portions of the Snap Lake data set. So in 99, they produced a publicly disclosed data set that goes from very small sample sizes or up to very large sample sizes, which overlays on their previous data sets as shown on this graph. A very, very interesting graph to look at from this perspective. The variability in your data is very high. The 1 sigma is very high at small sample sizes. As you approach roughly 100 kilos in this data set, that variability starts decreasing markedly. And as you go higher than that, it stays roughly the same. So the threshold for significance in terms of sample sizes at Snap Lake is somewhere above 100 kilos. Once you get above that, your data set starts becoming very predictable, very constant, and sample sizes do not have an influence on the amount of variability in results that you get. So this is an illustration of something that is a more general case in microdiamond sampling. Higher variance data can typically be ascribed to undersampling or small sample sizes. That's a very common issue, and it's very well illustrated by this data set. You can also get low count rates and higher variance at lower grades. Snap Lake isn't that low grade, so that's not a problem at Snap Lake. If you sample across domains or unit boundaries, that's obviously something that can lead to variability in your data set. There's something called intra-domain heterogeneity, which is not much discussed. It's very difficult to prove that without additional information, in particular geology. Outliers occur and they contribute to higher variance, and then there's these extreme outliers, which we call nuggets in a statistical sense. And we'll see the examples discussed further on about what these things do to your microdiamond results. So let's go look at some data application of how we use these benchmarks that have now been developed. We take some early Diavik data. This is 94, 95 drill core microdiamond data disclosed in a publication by Curtis Brett and colleagues. This is the data itself on the grade size plot in solid black over here with individual microdiamond counts per ton on a log scale in this dark curve over here. And you can see the distance between the data points on this curve is equal all the way across this range of diamond sizes, which in this case goes up to 1 carat. And so it's easy to fit a line through these because they are equally spaced in root to sieve classes. If you're looking for benchmarks to compare to the early Diavik data, the microdiamond data, then clearly this benchmark over here is not appropriate. You can see it actually diverges from the shape of this curve. That benchmark is not appropriate. And so you select 3 benchmarks. In this case, they're given in pastel colors here. There's a slightly purple one, light blue one, and a darker blue color. These 3 benchmarks look appropriate to compare to that curve. And when you do compare it to that curve, simply with the raw data as it's shown over
Herman,
here.
you're breaking up a bit. I don't know if it's at your end or our end. Maybe someone else can comment.
Oh, maybe I should stop my video. That helps. I was saying, if you compare this microdiamond curve for early microdiamond data to appropriate benchmarks, there are 3 benchmarks here, then you would forecast grades extending up this way of about 3 carats per ton with a very large error. That's the 1 sigma error expressed as a percentage of the grade. If you take the same data and you eliminate these 2 slightly aberrant data points, you get a much lower 1 sigma error, 10% or 8%, and a slightly lower grade. That's fairly obvious. These things are sitting on the high side of this curve, but a very consistent prediction. And it turns out that was very close to the mine grade early on in the Diavik, in the A154 North system. So in terms of using the benchmarking approach to forecast the recovered grades, it seems a reasonable approach to take. The trick about using that approach is that you get a handle on your errors. There's a very big difference to have a 30% error relative to a 10% error. And that's really the contribution that using benchmarks makes to the microdiamond exercise. In the same source, we also have data for Diavik A21, 170 kilo sample. That's quite a smaller sample. This is the same, this is the data set on the same graph. We've used the same benchmarks. And if you use them raw, you get these kind of grade forecasts with this type of error. And if you eliminate one of the data points, this one over here, you get the same grade range, but with a lower error. And it's because that data point lies off the standard curve. But if you use the benchmarking approach, you can identify that this is an aberrant data point and quantify the error reduction by removing that data point over there. So that's an example from Diavik. We can go to an exploration project. This was the Mackenzie project in the Northwest Territories. It was explored by Sanatana Diamonds at the time. Look at the sample sizes here. In 2007, they collected a ton of microdiamonds from the Dharma kimberlite, which was then discovered, and 450 kilos from Dharma Uttar. In 2008, this is the public domain, the microdiamond data that became available. It turns out we were able to use 7 different benchmarks to inform where this microdiamond data set is relative to those benchmarks. If you use just the raw data, the grades you would forecast would be these ones with extremely large errors. Those large errors are attributable to these outlier data points. Those over there. And if you eliminate them for the Dharma case or the Dharma Uttar case in open circles, if you eliminate that, your grade goes from 0.41 with a large error to 0.23 with a smaller error. And the same exercise for Dharma itself, which is the triangles. If you eliminate those 2 data points over there, your grade goes from 0.78 with a very large error to 0.33 with a smaller error. So you can pick your poison. You can either have a high grade with a high uncertainty, or you can have a low grade with a much reduced uncertainty. The way I use these data is I go for these results because they turn out to be more reliable. What we learned from this example is this whole process of discretization with the single stone data. Notice this was a 1,000 kilogram sample. So these triangles, which is from the STA Dharma data set, which is 1,000 kilograms, that's a ton. That's one diamond. That's one diamond. It's another diamond. It's single stone data. It's sitting on the larger sieves, and these are outliers. So we can formally highlight the outliers by calculating the variance associated with this data set. These are outliers. They're not nuggets yet. They're simple single stone outliers. It's a recognized problem in microdiamond data sets, and they contribute a remarkable amount of variance when you compare them to known benchmark curves. Here's another example, Newfield Resources from Sierra Leone. They've got a whole bunch of dikes, 2018 drill core microdiamond data. When you drill a dike and the intersection is fairly narrow, you end up with small sample sizes. All of these samples, microdiamond samples, are less than 100 kilos. They represent different dikes. There are 4 different dikes represented over here. And when you take small samples, you end up with noisy data. And that's what these curves are. These are 4 different dikes that have been drilled, and the data is noisy. It turns out there were 11 benchmarks available to us to compare against this data set. We chose to just use 3 of them. It spans a whole range. And when you do that comparison, you end up with a table over here. And by now you know what I'm going to do. I'm going to isolate the outliers, those 2 over there, that contribute a large amount of noise to these 2 grade predictions. When you eliminate them, the grade prediction changes, but it has much higher reliability. However, quite interesting, for the Kundu and Lando case, even though you took very small samples, I did play around with what potentially are outliers. The grade doesn't change that much. You do increase the resolution of your grade prediction, but not by much. And so outliers don't contribute a lot to the Kundu and Lando data sets, even though these were very small samples. That's just lucky. You can see the Lando case is over here. That's a fairly smooth curve. This is potentially the only outlier that, or data point that contributes to variance. The rest of this curve is quite smooth. And I'm getting to the end of this talk now. There's a new benchmark that's out there. In August 2018, Lucapa Diamonds put out a microdiamond data set for the Little Spring Creek lamproite that's in the West Kimberleys in Australia. That's quite an unusual data set. There's 1,100 microdiamonds larger than 75 microns in 177 kilos of core. There's the 75 micron bottom cutoff. Most of my benchmarks started, well, in fact, all of my benchmarks started at 106. This microdiamond data set on its own crosses a whole bunch of the benchmarks, and the implication is the extension would be somewhere down here. But I can only turn it into a benchmark once I have a macrodiamond bulk sampling result, which falls somewhere over here. And it took 100 tons out of there, recovered 11 stones plus 1 millimeter for 0.28 carats recovered. That's that data point over there. You can now fit the benchmark through over here, the whole lot. That's what it would look like. It would be unlike any other benchmark that we currently have in the data set. And so it's a very valuable benchmark to have for something that we wouldn't generally describe as a fine stone size distribution. In other words, very high counts in small sieves, very low counts in coarser sieves, and we're not even at a half a carat over here yet. So the projection of this curve to commercial sizes is not going to look that good. There's another interesting data set to discuss. This comes out of the Mateti dike in Lesotho. It was sampled in 2011 at surface. 7 samples, a total of about 1,400 kilos. These were 200 kilos each per sample, roughly. And it gave you a data set in triangles, which is largely hidden by a subsequent data set, but there it is over there. And it peaks out over here. Subsequently, they drilled this dike to depth to expand the resource. The dike isn't that small, but nevertheless, they only were able to recover 108 kilograms total out of 10 drill intersections. That was from core. That's in open circles. Perfectly matches the data for the surface sampling to depth. Brilliant data set to have. But there's an interesting interpretation in this case. In the background, there's a benchmark curve that fits this tangent over here. And that benchmark curve is 4.63 carats per ton. You would only be aware of that potential for this dike if you knew about these benchmark curves. And if you use that benchmark curve, your interpretation of this part of the data set would be that there's a systematic loss in the small stone size fraction, which is equivalent to diamonds being resorbed. And that's a repeat result. You've seen it from surface sampling, 1,400 kilos. You've seen it at depth from drill sampling, 108 kilos. I think that's very well substantiated. So I think that's formally the end of that talk. The topics that we've covered, it's very crucial to realize these Root 2 series square mesh sieve reporting standards that were implemented by the CIM in March 2003 have really standardized the microdiamond data set that's in the public domain. If you go through that data set and you start correlating co-located microdiamond and bulk sampling data, like I showed you for the Springs Keek lamprite, you can make up these benchmarks. If you use those benchmarks, and I always use 3 of them at least, you can calculate the macro grade and the relative variance. That's a key contributor to quantifying what's going on in your data set, and in particular identifying outliers and the effect of single stones on coarser sieves and what that has on your grade prediction. And it has a beneficial application in forecasting or auditing macro grades at various stages through the resource development cycle for primary diamond deposits. I'd like to acknowledge a number of people that were instrumental in my getting interested in microdiamonds. BHP Billiton really supported a rollout and embedding in their diamond program of microdiamond sampling strategy at a minimum 200 kilogram sample weight. Peregrine Diamonds introduced something called the Hornet reverse circulation rig in October 2010. There's a little Hornet rig. You could drill 2 or 3 targets per day with this rig, helicopter supported. And the drill product came at you, you collected it over here, underneath a cyclone. And there were a number of issues that we had to resolve about microdiamonds. One, when you use a hammer bit, as is the case with this RC drill rig, it's air supported, it's not water supported. There's the compressors. Do you see diamond fragmentation by the RC hammer bit? The answer to that is yes, you do. Do you see diamond attrition in the RC air blast slurry return system, this system over here? The answer to that is we don't know. Do you see fractionation or concentration of microdiamonds through the cyclone? Notice this cyclone is spewing out finer material as smoke in the chimney, and their finer microdiamonds may be coming up there because there's a cyclone over here, guys. And the coarser and heavier material is coming out over here. That's what we collect in our samples, and this stuff is lost to air. The answer to that is, indeed, there is fractionation of microdiamonds through the cyclone system, this air cyclone system. And so we were able to correct for that. What size and weight of an RC sample must be collected to constrain, a 50 carats per 100 ton grade potential to within a particular limit? That limit is one that BHP said we need our results to be accurate to this threshold, and it made me start thinking about 1 sigma errors in microdiamond data. So they had a big influence on how I view microdiamond data sets. Jennifer Pell was a research collaborator. She did a lot of sense checking of the public domain data. Cliff Revering, who's an SRK colleague and sounding board on how to use these data sets, also an important colleague at SRK. So thank you everybody for taking my career into a different direction here and applying my skills.
Any questions from those that saw the whole presentation?
And Herman, I mean, just to put some sort of financial perspective to it, I mean, what would a program and a very ballpark figure, cost to collect some of this data on, some of these kimberlites and in many cases several kimberlites, that you've done in obviously an Arctic or a Canadian context where, as you show in the picture, you've got to fly and take your whole kit and rig with you.
Yeah, look, just in round numbers, for the Chidliak project, roughly, if you all the camp support and all of that sort of stuff, if you average it out in a sampling program, a till sampling program for indicator minerals, we're talking 1,000 Canadian dollars a sample, processed with the results. So all in for that enterprise, $1,000 Canadian a sample. Microdiamonds is not, it's not that easy to give it a program-wide cost because
every sample is different.
Every sample is slightly different. But on a core drilling program, a 200 kilogram microdiamond sample is 50 meters of core, NQ core, and it may be distributed across, a much larger interval that you've drilled, but it's 50 meters of NQ core. That will give you 200 kilos, and it will cost you $110 Canadian per kilo to process. So, there's the drilling cost and so on, but to get the microdiamond result is $110 a kilo for 200 kilos. So that's $20,000.
Yeah, and that's Canadian dollars. So that round figure. I mean, that's plus 200,000 Rand per sample.
Yeah, but you heard Hilda Cronrate say 200 kilos. Yesterday, she said the cost to process 200 kilos through their lab was, she gave a figure, she said 400,000 Rand.
Yeah. No, it doesn't come cheap, but I mean, it's very powerful data if you collect it systematically and professionally.
Yes, look, it's become definitive. It's a standard for diamonds these days, in particular because of the reporting requirements and so on. It's if you're in this game and you're not collecting systematic microdiamond data, you'd be remiss.
Yeah, and I mean, just to add to it, I mean, you'd obviously be doing, the indicator minerals or the minerals and whatever else you can, including petrography on the same samples or portions of the samples.
Yes, the same samples or portions of the same sample, representative sampling is very important. But I just want to reshare a part of the last talk. John, the context for doing both microdiamonds and kimberlite indicator minerals is this context.
Yeah, absolutely.
Microdiamonds don't tell you where your kimberlite is sampling the mantle. They just tell you this is how many diamonds you have in per kilogram of rock. They don't give you this perspective. Right? Look at this perspective that you get from the kleiner pyroxene data for this particular kimberlite over here, which is why I put that diagram up earlier today. This perspective you can only get from the silicate portion. The microdiamond data don't help you anything in this space.
Yeah. No, you've gone to all that effort. You've got to throw the book at it.
Yeah, but you also learn a lot more about your kimberlite province as a result of looking at this part of the data set.
Herman, have you got data on the size distributions of peridotitic versus eclogitic versus sublithospheric diamond populations? Or I presume that's pretty difficult to get.
Yeah, it's quite selective. Actually, it turns out that most of the some of the best data on size distribution of diamonds in mantle xenoliths comes out of Derek Robinson's PhD. It's mostly Arapa eclogites, I think, if I remember correctly. The academics that study diamond-bearing xenoliths, they simply don't measure the size frequency distribution. They're not interested in size frequency distribution of mantle xenoliths. Although I have pursued, when I see a particular academic has studied a diamond-bearing xenolith, I've actually pursued that information on a semi-private basis from some of them. And that's why I was able to put that up for, you know, in the case of Tuawi, I have those examples. I know those numbers are good. But you have to, you have to do follow-up work, and Andy, you're no stranger to follow-up work. You follow up with people all the time.
Yeah. You know, I think one of the interesting things, you know, from the sublithospheric story for group 2s was that the sublithospheric stones had all come out of Juina, and they were very small stones, and you know, when they screened a large number of samples at the GIA, they pushed that sublithospheric population, whatever you might want to link it to you know, to much coarser stones. But the, you know, and of course Juina was alluvial, so I presume that complicated things as well. But you know, you get the impression that the clippers are going to have a distribution that's skewed towards big sizes, which is, you know, what you said in that graph. But it would be something worthwhile doing, you know, to try and get that, you know, get a systematic data set going for the different associations.
Yeah, look, you have to speak to the GIA for that. You know, people like me and you, we simply don't have access to those kind of diamonds, and that's why the study by Evan Smith, you know, is so seminal, because nobody else had access to that material.
Well, it asks all sorts of interesting questions, because there's, you know, the whole question of how you get a 10-carat stone. Some of those stones were going up to 10 carats. I don't recall what that actually had, but some of those sublithospheric stones were coming from 600 kilometers, you know, based on the inclusions. So that's asking all sorts of questions about kimberlite emplacement and how the hell do you get those things up to the surface?
Yeah, I'm not going to speculate on that. What I know is that they occur at surface.
And Herman, just a very general question. I mean, who's left driving exploration in Canada at this point in time? Is it still juniors or mostly?
Yes, there are some juniors. We can call them in Afrikaans bitter enders. Buddy Doyle is still doing stuff on the Slave. What's that? North Arrow is doing quite a bit of work on a very selective basis across large parts of Canada. There is new interest in Ontario, in some of the Ontario kimberlites. It's juniors again. Many of the more recent pieces of work are around established resources that were previously declared at inferred level. And then people taking that on and having another look at it. Much like the development was in northern Lesotho that started about 10 years ago.
Yeah,
it's a new look at old resources.
Yeah, and I mean, Rio is really just set on having a good look at Star, an existing project. They're not doing any exploration work.
Yes, that's correct. So that's yeah, I forgot about that. They're in the major space. Yeah, that's what Rio is. Yeah.
Yeah. Okay, mate. Maybe you want to just stop sharing your slideshow, and let's just have a quick wrap up. You mentioned some important references there. In due course, I'll come back to you and just get a list of the half dozen or so that are really critical, and we can circulate those to all the students and in fact all the audience. Some of us need a refresher as well. And
yeah.
And likewise, your YouTube clip of your presentation you gave end of last year on the microdiamond study as well.
Yeah, the most interesting part of that YouTube video is the
Steve Haggerty.
Is the intervention by Steve.
Yeah, it got quite colourful. Okay.
Herman, any comments on Victor, for instance? I mean, Victor was a very singular diamond population, relatively coarse, a few microdiamonds. In consideration of what you were saying about, many of those smaller diamonds coming from, I think it was peridotite nodules, whereas the coarser diamonds, the example you gave was coarser diamonds coming out of eclogite nodules. Yeah, so there's sort of several different sort of questions there. Let's just deal with coarser and finer diamonds. It's a general observation, and Farnes Viljoen has put that in the public domain, as did John Gurney initially, that diamonds that you find in eclogite xenoliths in general are coarser grained and in general of higher quality than diamonds that you see in equivalent peridotites. And more or less that is generally held out by the work that people like Jeff Harris has done through the years, and also that Thomas Stachel is doing. So it is a generalization, so you will get exceptions, but it's a very good and a very, very sound generalization. Now, how that actually applies to Victor, where we did see very coarse diamonds and of very high quality, without very many small diamonds, that's the domain of De Beers. That mine is now closed, and they have permitted publication of information which addresses that topic. And it's this diamond inclusion data set that's come out, but there are 5 other papers about
Diamonds from Victor, which discusses their carbon isotopes, when they grew, which they grew at 720 million years. That changes a whole lot of concepts that we carry from the Kabzal, and it changes it in this way. Basically, it's saying that diamond growth is a repetitive, is a cyclic situation. We can see many different cycles of diamond growth. The younger cycles of diamond growth are often associated with eclogytic dominated inclusions, and they are tied to geodynamic cycles. So the geodynamic cycle that caused 720 million year old carbon deposition in the central superior craton actually started at 1100 million years when there was a rift there, or a rift 600 kilometers south of there. And then that craton cooled and it was exposed to a new cycle of carbon-bearing fluids. And those provided the mineralization that eventually resulted in the Victor mine. So
yeah, that was, I mean, I'm really getting back to, Herb's presentation the other day, where he was talking about how the superior craton, was assembled and so on. And, it's just striking that Victor has, a different diamond population to what you would normally see, what we see in other kimberlites. Is it, it's not bimodal, if you want to put it like that. That's not the proper description, but
yeah,
it's very unique population.
I think the uniqueness lies in the fact that those diamonds grew very young.
Yeah. So that maybe has implications for the superior craton as well in terms of prospectivity. You're looking for a different type of animal.
Yeah. Yeah. Oh yes. There is a general lack of kimberlites on the superior craton, which is the biggest craton in the world.
Yeah, no, that's right. And Renard has got quite high quality diamonds as well, though not as good as Victor.
Yeah, there are some very high quality diamonds at Renard, but a lot of lower quality diamonds as well.
Yeah, yeah.
And Snap Lake, Herman, I mean, that was just the failure of that was just too complicated to mine. I mean, mining dikes is tough enough, as Jim will tell us. Jim, mining the sort of wandering soil was going to be doubly difficult.
The biggest issue there was the water.
Yeah,
it's underneath. It was underneath a big lake in a fractured terrain. And so that lake had many, many different ingress paths. And every time you took a ton out of a stope, it was replaced by huge volumes of water continuously. That was the biggest single issue.
Yeah. And there's an interesting question from Quinton, and I discussed it with him this morning. Information classification for Websterites. Do you have something you can send us? I mean, it's not the most sort of typical interesting mineral in the broader scheme of things, or not xenoliths.
Yeah, so Websterites have become a class of their own. They were originally sort of included in the diamond inclusion studies as part of the eclogite fraction.
Yeah.
But as people started recording more things that didn't quite look like eclogites, they then started classifying them Websteritic diamond inclusions. And there's actually a very good paper by Sonja Albach, and also Dave Phillips
started messing around with Websteritic garnets. And I believe also Farnus Viljoen has a very good paper on Websteritic.
Okay, good stuff.
diamond.
All right. We'll dig those out.
Yeah, so yeah, so they have come up of their own in the past sort of 15, 20 years. Yeah.
Mm.
So
just a comment on that is that you have the problem that chemically there's a strong overlap with the megacrystal suite, and I didn't put it up when I talked, but with those so-called Websteritic framocytes from the Vienna collection, if you do your magnesium titanium plot, it straddles, the megacrystal Websterite plot. So I think there's a problem using just a simple chemical criteria, or at least using chemical criteria to try and distinguish between megacrystals and Websterites. And but I think at least a fair proportion of the Websterites are going to actually be megacrystals.
Yeah, for sure. Okay, anyway, I mean, there are some people out there who worked on them, and we'll dig those out for you, Quentin. Any other questions?
Oh, I see Tabang has asked a question that's very difficult to answer. Tabang asks, hi Herman, may you kindly recommend any literature relating to the use of microdiamonds for geostatistical valuation? Tabang, I've tried to make my way through the available literature. The available literature is an academic literature. It's not a commercially applied literature. And it's so divorced from the microdiamond data sets that I'm used to working on that I ultimately gave up on how the academics look at the enterprise of microdiamond use from a geostatistical point of view. What I can recommend to you is Johan Ferreira has a PhD thesis that's available in the public domain. It's through...
Yeah, I've got a copy of it, Herman.
Yes.
I mean, I'd gladly circulate it. It is available if you Google it as well.
Yeah.
Yeah.
And it's a very good summary of where we are. And Johan obviously has had a long history of actually dealing with the practical side of microdiamonds. And describing that from a geostatistical point of view. So it's much more useful in terms of the diamond industry and in an applied sense to go to that work than to just simply go look at what academics say about the enterprise.
And I think to add to that, I mean, as you've done, you've actually got to work with the data and go and plot it and play with it. And probably also listening to your talk of late last year, will help as well. So we'll circulate that to everyone. Just trying to learn microdiamond sort of trends and data from the books is very difficult. You actually need to be working with the data. I think that works much better in my limited experience anyway.
Yeah, and it's a whole different ballgame working with data on a log plot. Wow, it really does change things.
And in fact, it's been useful in the alluvial business to, study populations. Again, it's a log plot, and obviously it's a slightly different population, but it goes back to your point as well that, similar deposit or an individual deposit has quite a distinct size frequency distribution, and it's useful data. So that's another way of coming at it in the broader sense.
Well, John, the thing about alluvial diamonds they are well sorted.
Absolutely, yeah.
Okay, so if you want to look at size frequency distributions and you want stable data, the place to go is the alluvial data sets.
Lyndon, you're on the talk. You're going to presumably throw in a few next week as well. Anyway, so there should be some of these interesting plots come up from the alluvial guys. Lyndon and ourselves put together a lot of good data over the years, and it's very useful.
And I see that Jan Stephenhofer has given us quite a useful background comment on Snap Lake, and again, it just brings you back to mining these things is always a practical financial challenge. So, it gives some very good background there, a bit more than just the water.